Hello, everyone. Welcome to another calculus analysis problem at graduate level. Please subscribe to our channel, and also you can follow us on Twitter and Instagram to be updated of our new videos instantly. With that said, let's look at this problem in detail. You begin with some positive number, real number, and then you define recursively a sequence by xn plus 1 equal 1 over 1 plus xn. Prove that xn is a convergent sequence. Now, I'm going to present two solutions, but the first one will be only a sketch because I believe that the second solution is quite elegant. For the first one, I claim that, let's say x1 is bigger than 1 or bigger than some threshold. Then your even sequences, that is your x1, your x3, your x5, your x6, these red ones will form a decreasing sequence toward the limit x0. And then the even ones, x2, x4, x6, x8 will form an increasing sequence toward that same x0. So together they will combine into a convergent sequence. If you start with a small x1, then these roles will switch and your odd sequence will be increasing and the even will be decreasing. Why this happens requires some, of course, calculations, which will be kind of buried inside the calculations that I'm going to do for solution number 2. So what is the idea behind solution number 2? The idea is that the sequence I have, which is xn plus 1 is given by 1 over 1 plus xn, is equal to f of xn, right? Where f of x equals 1 over 1 plus x. Okay, so notice that we have this. Now, we've seen sequences defined by such recursive things in the context of fixed point theorems. You begin with any point in your complete metric space or compact metric space, and you reiterate by applying f again and again. And the claim of the theorem is that you approach a fixed point. So in this case, it would mean that xn converges to a limit point, which is the fixed point of f of x. However, we need to fix a couple things. So f, where is f defined? Your x1 is from 0 to infinity, which is not compact, which is not a complete metric space, because 0 and infinity are excluded. However, the following trick works. For the time being, so for now, restrict f to 1/2 to 1, closed, as your metric space x. So my claim is, remember, if you want to prove a fixed point theorem, your map must go from your space back into your space. So it would be a disaster if you mapped this 1/2 1 and the image was completely outside this interval. Well, proof of this claim is that, so let's see. You pick x from 1/2 1, and then you plug that into 1 over 1 plus x. So what is the biggest you can get for this quantity? The biggest is when you put the smallest in the denominator. So this will be 1.1 plus this, and this is 2/3, which is definitely less than 1. On the other side, the smallest fraction you can get is when you put the largest in the denominator, which is 1, x being between 1/2 and 1, and this is again 1/2. So this shows that indeed f does map from X back into X. So that is your f. X is a compact metric space, which makes it definitely a complete metric space. You start with some point, you plug into X, and you reiterate. So you look at X, f of X, f of X, and so on, which is exactly how our sequence is defined. And what is the other condition we need to make sure that this sequence converges to a fixed point? The condition is being that if we must show is a contraction map. And by that, we mean that if you compare the distances of images, they get closer. So we have to find a bound on how far away fx and fy can be. Of course, x and y are from your space X. So fix these two guys in your space. F of x minus f of y is 1 over 1 plus x minus 1 over 1 plus y. And this is equal to 1 plus x times 1 plus y. No need for absolute value up here. But how large can this denominator be? Or how small can it be? Well, the tiniest x and y you can plug in is again one half. So you get that f of x minus f of y is smaller than or equal to 1 over 1/2 twice times x minus y. And this guy here is definitely a c, which is less than 1. And that proves the second claim that f is a contraction. So by fixed point theorem, the stronger statement of the theorem, not just that a fixed point exists, but that beginning with any x1 inside your x, x1, f of x1, f of x1, and so on, converges to the unique fixed point of f. Of course, this sequence is nothing but the sequence that we started with. That means this sequence is nothing but x1, 1 over 1 plus x1, which is your x2, and then 1 over 1 plus x2, and so on. Just that is how f is defined. The problem now, have we solved the problem completely? No, because if I pick from within x, I'm good. But in the initial problem, I picked any number x1 between 0 and infinity. Is that a problem? Not too much. If x1 is between 0 and infinity, then x2, which is 1 over 1 plus x1, is, where can it be? So the biggest you can get is 1. That is when you plug in 0 for x1. And the smallest it can get is when you, so is 0, because x1 can be as big as we want. So x2 is in this range. So x3, which is 1 over 1 plus x2, is in the range. So again, the largest it can get is when you plug in 0 for x2, which gives a 1. What is the tiniest value for x3 we can get? that is when you plug in the largest for x2, and x2 can be as big as 1 but not bigger, so it becomes 1 over 1 plus 1, that is 1/2. And I'm generous, I include the endpoints, so it happens here. And now this is exactly your space X. What happens is that now x3, x4, x5, etc. converges according to above. And that's the end, because you can ignore x1 and x2 and look at the tail of the sequence. So convergence doesn't regard the initial several points. So that's a beautiful application of a fixed point theorem to a concrete example of convergence of sequences. Does one have to know this much analysis to prove that this sequence converges? No, but writing the proof down using the solution one idea can be quite lengthier and messy. You have to compute this x0 precisely. So this is √5 minus 1 over 2. And you have to look at cases when x1 begins above x0, the case when it begins below x0, and whatnot. So if you liked the video, again, please like and subscribe to our channel and follow us on Twitter and Instagram as well. See you in a future video soon.